the JK flip-flop having two inputs, so the total number of minterms will be 2 to the power 2 plus 1, and that is going to be 8. So the total number of minterms will be 8. Okay. Now, here is the table. Yes, because all the minterms are already ready. So up to this QT, we can make it. It's fine. So that is why I have already prepared it. Okay. Because this is nothing but this is a sequence of digits which we have to follow. Now, to prepare this QT plus 1, I should know the characteristics table of this JK flip-flop. Okay. The characteristics table of JK flip-flop looks like this one. Okay. So the characteristics table of JK flip-flop will be like this. So let us try to fill it up. Okay. If J and K are 0 and QT is equal to 0, 0, 0 and 0, that gives you the 0. 0, 0 and 1, that gives you the 1. 0, 1 and 0, that gives you the 0. Then you will get 0, then you will get 1, 1, 1 and 0. So this is the table that I have to make it. This is that table has been prepared with this characteristics table of the JK flip-flop. This column has been prepared with the help of this table. Okay, because we have already done this thing before, so I do not need to tell you how we have got it. Now, once we are ready with this QT and the QT plus 1, okay, now I have to use the excitation table of the D flip-flop. Okay, so the excitation table of D flip-flop, and that we know that the excitation table of D flip-flop looks like this one. Okay, so let us try to see how the excitation table of D flip-flop can be utilized for that purpose. Excitation table of the D flip-flop will be like this: 0, 0, 0, 1, 1, 0 and 1, 1, and with the help of this one I need to find the D. So here I have a 0, 0. For 0, 0, D will be 0. For 1, 1, it will be 1. For 0, 0, again it will be 0. For 1, 0, for 1, 0, I need to get it 0. For 0, 1, it will be 1. 1, 1 will be 1. 0, 1 will give you 1. And 1, 0 will give you 0. So this is how we can prepare the input table for the D flip-flop. Okay. Now, once we are ready with this one, what I have to do, the next step is to make the K map of this D flip-flop. Okay, K map for the D input. Okay, the K map for D input need to be prepared. So this will be the input will be J, K and the QT. Okay, so these three are the input, and I have to prepare it for the D. Okay, so if we try to see how it will look like, how the K map can be filled here. So it is 0, 1, 0, 0, 1, 1, 1 and 0. Okay, now the next step is I have to make the pairing. So if I can see this K map, there are two pairs which are possible. One pair is this one. Okay, and the second pair that we can make is this one. Okay, here I'm not considering about the hazard and other things. Okay, if we are considering hazards, then in that case you have to use the redundant pairs as well. But here I need a simplified circuit. Okay, so if I have to make, like, the question could be yeah, this is really very important. If the question is like convert a D flip-flop to JK flip-flop, and the circuit should not have, the flip-flops must not have any hazards. Okay, so in that case I need to consider this redundant pair as well. But because I need a straightforward, so in that case I do not need to use the redundant one. Okay, so I have only two possibilities that I can make the pair, and this is how we can do that. If we are ready with this pair, let us try to see what is the output function. Okay, so the output function or this D which is like given here, D is a function of J, K and the QT, and this is nothing but, if you try to simplify it, from here J will be cancelled out and I will get K bar into QT plus in the next pair I will get J into Qt bar. Okay, so this will be the output function, or the simplification of this K-map. Now what it means? It means that D input will be connected with the two of the inputs which are J and K, like this kind of arrangement. Okay, so for that purpose, what kind of logics I need? How many logic gates I need? One logic gate is needed for this K complement. Okay, so that is inverter. I need one AND gate for this operation, and I need one AND gate for this operation, and then I need one OR gate for this one. So in total, I need 4 logic gates, one inverter, 2 AND gate, and one OR gate. Okay, so these kind of logic gates are needed to implement it. Okay, so let us try to implement it. So see here, the first thing was the K complement. So here I have a 2 inputs J and the K. So I need one K complement and I need to AND it. So here K complement and I need one AND gate. So I will get the K bar QT. Second one is JQT bar. We need JQT bar. So J is here and Q bar is here. So I need to AND it to get it. Okay, and then I have to use one OR gate to that need to be connected to the D input, and this is the circuit that will give you the function like JK flip-flop with the help of D flip-flop. So similar kind of approach can be applied to any of the logics. Like see, as of now we have studied 4 different kind of flip-flops. So any kind of conversion is possible. So I have done 3 conversion. I recommend you to just follow the same procedure to convert rest all other possibilities. Okay, so just do all these things at home. Yes, while converting or while designing this flip-flop, you need to keep 2 things in our mind. If in the problem it is not given what kind of clock is there, so you can use any one. Okay, so this is the first thing. Second thing, if it is given, then definitely you have to make the clock arrangement as per the problem statement. Second thing that you have to consider is like if the conversion, if in the problem it is not written like it should be the hazard free, so you can use a normal one. You don't need to use the redundant pair. Okay, but if in the problem if it is given like you have to make the converted flip-flop that should be the hazard free, in that case you have to use the redundant pairs as well, which we have already done before. Okay, we know that how to remove the hazards in the logic. Okay, so you have to apply all the those regulations here as well. Okay, so please try to solve rest of the problems, and that will help you to understand the actual things. Okay, let us consider a few more examples related to the flip-flops. Okay, so suppose I have a circuit, or I have a flip-flop. This is a T flip-flop, and this T flip-flop input is controlled with the clock pulse. Okay, and if we try to see here, this flip-flop is nothing but this is the positive edge trigger. How we identified? Because here if you see triangle is given and there is no bubble, what it means? It is the positive edge trigger. Now what is the problem? Problem is what is the frequency of output pulse of the circuit using T flip-flop, whatever. So I need to find out what is the output frequency. Okay, so let us try to see here. I know that to get the Qt plus 1, what is the output? I need to use the characteristics equation of the T flip-flop, because the T flip-flop is given over here. I know that Qt plus 1 for the T flip-flop is nothing but this is T XORing with the Qt. Okay, so whatever the Qt I have, that will be XOR and that will be the qt plus 1 will be there. Okay, so let us try to see how it will look like. Okay, so see here, suppose I have an input something like this, input t, and this is same as the clock pulse. Okay, t is like this, and it is the positive rise, a positive age trigger, so the rising is at this stage. Okay, so let us assume this is the clock frequency of the input t, which is the same for the clock pulse. Okay, whatever I have given. Okay, and this is activated at the during positive rise. So let us assume the time period of the clock signal, whatever I have provided over here. Yeah, similarly, here I will have a differentiator circuit, and here I will have a clock pulse, and at this stage I will get the spike kind of things. Okay, and here this will be the nothing but this is the differentiator. Okay, so this is what we already know. Now let us try to see here. If yes, see, qt plus 1 is nothing but is a t XORing with the qt. So see here, if the t is equal to 0 and the qt is equal to 0, so what will be the next state that you have to XOR it? And so similarly, after considering these things, you will get something like this. So what is the qt plus 1? That simply is nothing but this is the XORing of qt and the t. Okay, so the qt plus 1 that depends on the this one. Yes, one more thing. To get this one, let us assume this is the qt plus 1 expression. Let me assume this one. So this, to get this 0, yeah, so if you can go back one clock previously, so here I was getting logic high, and here the previous state is, yeah, this state is 0, so this is 1, this is 0, so that will reflect you to this state. Let me repeat it again what I'm saying. Okay, this is one important thing. Let's leave this first state. If I have to get this value, I have to get the value of this one, so I need to consider what is the current t and what is the previous q. Okay, so I have to XOR this one with this one to get this one. Okay, so this and this will be XOR to get this one. Similarly, to get this one, what I have to do, this state will become the previous state, and this is the clock 1, 0 and 0 1, something like that. So this is how it will follow. So on next clock pulse, that will be considered. So if we try to simplify this one, the output will look like this one. Okay, and if the output,
can you repeat, sir?
Okay, so simply if you can see here, qt plus 1 is nothing but is a t XORing with the qt. Okay, this is how the t is changing. Okay, t is initially 0, it is 1, then 0 and 1 and so on. Okay, and if I have to consider the what is the qt plus 1, so to calculate the t qt plus 1, yeah, so this is the qt plus 1. Let us assume initially this was the qt, and this is nothing but this is the qt plus 1. Okay, so to get the qt plus 1, what I have to consider? I have to consider the qt and the t. So this will be the qt that I have to consider, and this is the t which we have given over here. So t here is 1 and qt is 0, so that I will get logic 1. Okay, so logic 1 will be here. So qt plus 1 will become logic 1. Now again, in the next clock pulse, I need to consider the next thing. Okay, so see here, if you see at this stage 1 and a 0, 1 and 0, that will give you the 1, and the similar kind of procedure that you have to follow to get all these values. So the important thing is to get the qt plus 1, I have to consider the previous qt and the current t to get the qt plus 1. Similarly, this and this will be considered to get this value, and so on. Okay, so this is how you are getting the output of this circuit, and that looks like this one. You got the point?
Yes, sir.
Okay, so once we are ready with this flip-flop, this output, now let us try to see. The exact clock period of this, the clock period was t initially. Okay, and that was passed through a differentiator to get the positive one. But yes, of course, the time period of this clock was t, but at the output we are getting the double time period. And if I am getting double time period, what it means, the frequency will be half. Okay, so the output frequency of this circuit will be half than the input clock pulse. And this is the answer of this problem. So one very important thing, the similar kind of approach you can apply for all other gates, all other flip-flops as well. And you will get to know that the output frequency is always half than the clock frequency. Okay, that is why flip-flop is also known as frequency, the frequency divided by two circuit. Frequency divided by two circuitry you can design with the help of normal flip-flop. So suppose you have a clock pulse having certain frequency, and you want to get the half frequency than whatever we have, just pass it through a flip-flop and you will get the half frequency. Okay, so whatever I did for the T flip-flop, the similar approach you have to do for the other flip-flops as well, and you will get to know that what is the output frequency of all other gates, all other flip-flops as well. Okay, so this is the homework. Just do it for other flip-flops as well, and try to check it out. What is the frequency of input clock, and what is the frequency of output one? Okay, and you will get to know that the output frequency is always half than the input one. So that is why we can also say that the flip-flops are the frequency divided by two circuit. Okay, so this is really very important. So the answer of this problem is like the frequency is getting half. Okay, any doubt at this stage? If you have any doubt, you can ask the questions, otherwise we can move ahead. Okay, so here one more example here. The construct truth table for the sequential circuit shown in the figure determine the working of the final circuit. Okay, so any kind of logic can be given. Yeah, why I'm just showing all these kind of examples, because this kind of problems can come into the gate exams. Okay, so you should know how we can apply the fundamental of flip-flops to get actual truth table or other things. Okay, so let us try to see here. We know that the S, if you can see here, okay, so the characteristic equation of, yeah, see here, if you see this J is nothing but J is equal to X XORing with QT. Okay, this is the J. And similarly, if we talk about the K is nothing but X XNOR with QT. Yeah, what I have done here, this inverter is there, so we can say it is the XNOR logic. Okay, so we know that the characteristics table of the JK flip-flop is nothing but this is like QT plus 1. Characteristic equation is nothing but QT plus 1 is equal to J QT bar plus K bar QT. So this is what we already know. What is the characteristic equation of JK flip-flop? So the first step, like what is the expression of J and K, that I have to write. The second step is to know the characteristic equation of the JK flip-flop, which we have already here. Okay, once we know all these things, so what I have to do, because I know what is the J, what is the K, and what is the characteristics equation of the JK flip-flop. So what I have to do, I have to simply substitute this value of J and the K from here to here. Okay, so let us try to substitute it. Okay, so after substituting, what will be the expression? Let us try to see here. Qt plus 1 will be Qt plus 1. This is equal to J, and J is nothing but this is the X nor Qt bar. Okay, X nor, no, X, oh, sorry, not Qt bar, Qt, X nor Qt, and then I have to multiply it the Qt bar. Yes, so this is Qt complement plus K bar. Here I have a K, which is the X nor Qt. So the K bar is nothing but this is same as the X XOR Qt. Okay, because here this K is nothing but is a complementary of J. Okay, so I can use the same function what I have used for the J. So that will be like X XOR Qt into Qt. Okay, how I got this one? To get this one, this is nothing but this is, here I need K bar, and K bar is nothing but this is the J. So that is why I just wrote the same expression. Okay, now the next step is, let us try to simplify it. Okay, if I am simplifying it here, what I will get? The Qt plus 1, like here X nor X XOR Qt is common from both, and here I will get Qt bar plus Qt. Okay, Qt bar plus Qt, and the Qt bar plus Qt, that will give you the 1. Okay, one logic 1 will be there. So the Qt plus 1 that I will get here, Qt plus 1, that will be nothing but this is the X XOR with the Qt. Okay, so if I can find the table for this one, so let us try to fill the table. X can be 0, this could be 0 0 1 1 0 1 1. Okay, so this is the one of the possibilities, and if you see here, J is nothing but we just saw here, J is X XOR Qt. So the table of J will be like 0 1 1 0, because we are XORing it, and K is nothing but we are XNORing it, so that will become 1 0 0 1. So this is the table. Now I have to find the Qt plus 1. Qt plus 1 is nothing but this is the X into Qt. So X into Qt means what? X XNOR into Qt. X XOR into Qt means that will give you the 0 1 1 0. And if you try to compare this one, the Qt plus 1, that we are getting it just like a characteristics equation of the T flip-flop, because we are XORing it. Okay, so what it means, the final circuit, whatever we are preparing here, whatever the Qt plus 1 we are getting based on the input and the Qt, that is nothing but this is the T flip-flop. Okay, T flip-flop. So the final circuit, whatever we have made over here, is nothing but this is the T flip-flop with the help of JK flip-flop. Okay, so this is how we can understand or determine the logic circuit. Okay. So if you have any doubt, then you can ask the questions. So this flip-flop, this is nothing but the circuit is final circuit is T flip-flop. Okay. Let us assume I have a problem, something like this. Okay. What this problem says? This problem says, write the characteristic equation of the flip-flop for the circuit diagram shown in the figure. Here is the circuit. Okay. And I have to write the characteristic equation of the flip-flop, whatever I can see here. Okay. So let us try to solve it. If you can see here from this one, I can see the S is nothing but this is same as X plus Y complement. This is the NORing. Okay. Here, if you see the R is nothing but R is equal to Y plus Z complement. So this is how the S and R will look like. Now let us try to see what is the characteristic equation of the SR flip-flop. So let us try to write few things. Sorry. Characteristic equation of SR flip-flop. Okay, what is the characteristic equation of the SR flip-flop? It is it is something like, we know that QT plus 1, this is equal to S plus R bar QT. Yeah, if you can recall, this is the characteristic equation of the SR flip-flop. Okay, if this is the characteristic equation of SR flip-flop, and one more equation is there, S into R, that should be equal to 0. So this is what we have already studied. The characteristic equation of the SR flip-flop is which we have already developed before, and that QT plus 1 is nothing but this is S plus R bar QT, and SR is equal to 0. If we try to put above those values, S and R values in this equation, then what I will get? I will get something different kind of equation. What is that equation? Let us try to see. QT plus 1, that will give you S. S is nothing but X plus Y complement plus R bar is nothing but Y plus Z into QT. So this is the first equation that we should write. Okay, this is the first equation, and the second equation is SR is equal to 0. And after putting at this one, SR is equal to 0, what I will get? I will get something like, yeah, so if I'm putting SR is equal to 0, that will become S is nothing but this is the X plus Y complement into Y plus Z complement. So now I have to apply one law here. If you try to simplify it, that you will get is equal to X bar into Y bar Z bar. This is equal to 0. So this is the second equation that I have to get it. Yeah, this I have to apply some Boolean's algebra, Boolean's law to simplify it, and you will get the X bar dot Y bar dot Z bar. So this is how the characteristics table of the given circuit will look like. Now, what I have to do, if I have to validate how it looks like, what is the function of this circuit? So simply I have to make a table X, Y, Z and the QT, and then you will get the QT plus 1, and accordingly after solving this one, you can get like what kind of logic it is acting. So this is how it is doable. If you have any doubt, you can ask the questions here. Anyone? Okay, so if there is no doubt, then yeah, so here I have one tutorial question that that you have to solve based on the learning today's learning, whatever the things we have learned. Try to solve these things. So a new clocked UV flip-flop, UV is just a random name, is designed with two inputs U and V. The flip-flop functions are stated below. If U is 0 and V is 0, then flip-flop is set, then toggle, hold, and reset. Then what you have to do, you have to obtain the truth table, write the excitation table, obtain the characteristic equation. So this is what you have to do at home. Okay. So this thing is important actually. Just do it. Maybe you will be able to do that. Okay. Yeah, some important tables that we should know, because see, in this flip-flop designing part, in this lecture, we come up with the very important tables. Two tables that are the characteristics table of all the flip-flop and the excitation table of all the flip-flops. So you should remember these two things, because these are really very important, especially on the flip-flop designing or the counter designing or other things. So these two tables are really very important. Okay, so you have to remember these two things. Okay, and